If we have a circuit consisting of a series combination of a capacitor, an inductor, and a resistor, and some sort of a source, and some sort of a time-varying source, so that the source voltage is a function of t, well, there are a couple of principles we want to think about. The capacitor is going to tend to have a current that lags the current, or lags the voltage of the source. The inductor is going to tend to have a current that moves ahead of the voltage of the source, and these two are going to have opposing tendencies. The bigger the resistor, the more it limits the effect of the inductor, because a higher resistance is going to limit the current. It's also going to limit the amount of charge you put on the capacitor, but it has substantially different effects on the capacitor and the inductor. Again, not going to talk too much about the physics of that, but once you know the physics of what's going on, you can understand how it coincides with the mathematics that we're going to get when we analyze this sort of a circuit. Now, the voltage, and again, this is a physics principle, it's just energy conservation. If you move from one point to another, you don't change the potential energy, and voltage is just related to change in electrostatic potential energy. In a way, you'll understand if you know the physics. If you don't know the physics, the principle is simply that the voltage of the source is going to be equal to the sum of the voltages of the series circuit elements, the sum of the voltages across the circuit, the circuit elements in a series circuit. The voltage across a resistor is nothing but the current times the resistance. Voltage across a capacitor is nothing but the charge on the capacitor divided by the capacitance. And the voltage across the inductor is just the inductance multiplied by the rate of change of the current. Now, the current in this circuit, basically this circuit is just transferring charge from one plate to the other of the capacitor. So the current is just the rate of change of the charge on the capacitor, so that the di/dl we see here is just the derivative of the current. And let's back up right there. It's not di/dl, it's di/dt. It's the derivative of the current with respect to time, not the derivative of the current with respect to the fixed inductance. I was anticipating this development here when I wrote that, so let me fix that quickly. Okay, now we have time derivatives of the current. And the derivative di/dt, again, if I is the time derivative of the capacitor charge, then the time derivative of that is the second derivative of the capacitor charge, which leads us to this equation. Since L, R, and C are constants, this is just a second order differential equation with constant coefficients, and we have a non-homogeneous term over here, which is our driving voltage, source voltage. So all we have now, this is simply a linear second order differential equation with constant coefficients, and it's a non-homogeneous equation. So we have this equation that can be written like so. I divide through by L and get this form of the equation. Now, as we said a little while ago, this is of the same form as the equation that you would have for damped harmonic motion. The equation that we should be familiar with now, where the K is analogous to 1 over LC. The delta, the drag coefficient, is like the R over L. And you can understand how a resistance does put a drag on what's going on in the system. The effect of L in the denominator here is also important, but I'm not going to try to discuss that right now. And the solutions of this equation proceed almost exactly as the solutions of this equation. And I'll write down this equation, which is very much like this equation or this equation. This is the general form of the non-homogeneous second order linear equation. The solution method is identical. We assume a characteristic we find a characteristic equation assuming q equals e to the lambda t. We used e to the rt previously, but since I've got an r in this equation, I'm going to use lambda. If we substitute this into the equation, into the homogeneous equation, setting the right-hand side equal to 0, we get this equation with this pair of solutions, unless this discriminant here happens to be 0, in which case we have a kind of a critical case. If this discriminant here is positive, which occurs if this term is bigger than this, and that occurs when the resistance is greater than 2 times the square root of L over C, as you can easily verify by solving this inequality for R. If R is greater than this, you have real solution. If R is less than this, you have two complex solutions. And as you should understand by now, the complex solutions are the ones that lead you to the oscillatory behaviors, the sines and the cosines. And it's those behaviors that are of general interest in the analysis of circuits. Now, we're not going to go on with this. This has just been included and presented here to make the connection between the analysis of circuits, alternating current circuits most specifically, and the differential equations that we've developed in this chapter. And this will conclude our discussion of second order linear equations.